Another really cool example of symmetry and how that can affect the way quantum mechanical systems behave is rotational lines of molecules. So the theme here is that symmetry is intrinsically tied to the issue of indistinguishability of objects in quantum mechanics. So if you remember, the requirement of the exchange wave function for fermions is that the wave function psi1, 2, function of two objects, 1 and 2, is equal to the negative of the wave function for psi 2, 1 if I exchange those two. So that's the situation when we have these objects we call fermions. And then now let's look at a system where we take carbon dioxide. We've actually mostly dealt with diatomic molecules in this class, but here's a triatomic. And just for the fun of it, I'm going to take isotopically labeled carbon dioxide and put 18 oxygens out on the end there, 12 carbon in the middle. But the important part is I have two 18 oxygens on the two ends. So they're identical, and I cannot tell them apart. Now, to determine the moment of inertia of this system, the general formula for the moment of inertia of a system is actually the sum of the masses of individual objects times the distance squared from the center of mass of the system to the object. So that's the same as our expression reduced mass times the total bond distance squared, where we made this funny definition of reduced mass m1 m2 over the sum of the masses for a diatomic. You can easily determine for yourself that this is true for a homonuclear diatomic, where the distance from the center of mass to an individual nucleus of the two is equal to half of the bond distance. Then I take that and I square it, so I get 1/4 of the bond distance squared. And I have one of the masses out on one end, and so I have a 1/4 mass times that distance squared. And then I have the other one on the other end, so that's another 1/4 mass times that distance squared. There are two of them, and so overall I get 1/2 times the mass times the overall bond distance squared. And so I have a 1/2 mass, and if I look at the reduced mass of a symmetrical homonuclear diatomic, I've got mass times mass over mass plus mass is 1/2 the mass. So it clearly works for the diatomic case, and it does in fact work in general. But the general formula for moment of inertia is find the center of mass and add up the sum of all of the masses times the distance from the center of mass to those individual masses. So for 18 oxygen, this is about 18 AMU angstroms squared times 2, because the distance is about 1 angstrom. Always bonds are about an angstrom, and I got a mass 18. So I got about 36 AMU angstroms squared. And if you remember, the B value is 16.87 over I, and that's relatively close to half a wave number. Now the important number for rotations is 2b. If you remember, the line spacing for rotational transitions is twice the rotational constant. 2b is about 1 wave number. So we expect, if we look at carbon dioxide rotation, that we would find lines that were spaced about 1 wave number apart. Well, we can do this. We look in the mid-infrared at the asymmetric stretch of carbon dioxide. So one oxygen moving out, the other one oxygen moving in. That's roughly at 1150 wave numbers, to the best of my recollection. And if we look at that, so that's a vibration, but it also has a rotational transition. If you recall from Unit 2, we can go from J equals initial to a final number, either one larger or smaller, and get our P and our R branches out of this deal. And that spacing between those rotational lines is going to be equal to, we think, 2b. So when you look at that, and you look at carbon dioxide, you find that it's actually 4b. And the reason that it's 4b is because for this symmetrical system, instead of rotating through 2 pi to get back to where I started, I only have to rotate through pi. I only have to rotate carbon dioxide through 180 degrees, and I'm back to where I started. I have an 18 oxygen next to a carbon, next to an 18 oxygen. I can't tell the difference. And so the size of the world for the system, instead of being 2 pi, is pi. I've made the box half the width. And if I make the box half the width, Remember the energy spacings in a particle in the box go like length 1 over L squared. So the individual lines are 4 times, the energies are 4 times as large. And if you work it out, it turns out that the line spacing doubles in the system. So instead of 2b, I get line spacings of 4b. And that is entirely because of the symmetry requirement that you cannot tell the two 18 oxygens apart. And it shows up in the line spacing. And it gets even weirder. So if we change one of those oxygens to a different isotope, let's take the dominant oxygen, oxygen 16. So now I have asymmetrical O16, C12, O18. I can tell that apart. If I turn that 180 degrees, the O16 is on the right, not on the left. That's different. I have to come around a full 360, a full 2 pi, to get that system to be back to where it started. And lo and behold, if I look at this stuff in the infrared, the line spacing is twice b. I get twice as many lines because turning through pi is not getting back to where I started. And that's actually true. You can look at these things and find it, and I think that's incredibly cool. So there are other examples of symmetry in molecular orbitals. And one system that you're quite used to looking at is hybrid orbitals when we have things like aromatic structures. So we get a resonance structure between these two trihexene rings that we call benzene. So I can have the double bonds in one position or the other, and instead of having those two trienes, instead I get a fully delocalized aromatic structure, which is the more stable version, and then a fully essentially radical structure, which is the unstabilized, the destabilized version. And that's the stabilization associated with making aromatic rings in organic chemistry. That's the same deal. If I take the nuclei, I take all of those atomic orbitals and I lay them on top of each other. They all have basically the same energy, and I've got to resolve this fact that they all have the same energy in ways that respect the symmetry of this 6-carbon system, and I get that splitting. In general, with conjugated double bonds, I can write out, which benzene is an example of, I can write the system out like this, but if we look at those p orbitals, I can arrange this so all of those p orbitals are aligned with each other, and I get this beautiful molecular orbital that's totally delocalized, where there's really no there are no nodes other than the nodal plane of the system, and so the electron's free to roam through an enormous distance. And as we know, the wavelength is related to the momentum. The longer the wavelength, the lower the momentum by the de Broglie relation, and of course energy is related to p squared, so it goes like 1 over the wavelength squared. 1 over L squared in a particle in the box is the energy levels. Again, we just saw that with a rotational problem. And so as I make a conjugated double bond system longer and longer and longer and longer, that characteristic length gets longer and longer and longer, and that's because I'm able to make a wave function for this system that has a longer wavelength. And a longer wavelength is lower kinetic energy, is a lower energy, and that's the stabilization associated with conjugated double bonds. And in fact, you can model this thing like a particle in the box. It's got some length, L, which is related to this sort of string of bonds that I set up, and the energy of those electrons can well be modeled like a particle in a box. In general, however, whenever I set up these systems, I have some basic description, zeroth order description of the Hamiltonian, of the potential for the system, and then some complicated things enter in that we call a perturbation. And so I'll have some basic initial guess at an energy, and then this thing we call the perturbation Hamiltonian, which is the interaction that I left out. As an example, whenever we're thinking about how these orbitals interact with each other and hybridize, my zeroth order solution is just the atomic orbitals. And then I start building them together and adding them together, and the addition of this becomes this perturbation term. Fundamentally, the perturbation is how I adjust the energy when I start with two systems, two wave functions that are guesses, and we're calling them phi j and phi k here. And then I add in this interaction. Now initially, in the best of all possible worlds, of course, the basis functions for these systems are orthogonal, but my first guess at these basis functions, at these wave functions, probably won't be orthogonal because I left out the interactions associated with that perturbation. Now, as long as the perturbation respects the symmetry of the system, however, I still fundamentally have an integral that involves these two functions, phi j and phi k, interacting with each other, these two wave functions. And the really big deal is there's associations, there's things having to do with symmetry there. So if those two functions are geometrically orthogonal, in other words, if they have different symmetry, then unless that perturbation Hamiltonian is really weird, we're basically guaranteed that that perturbation term is also going to be zero, because phi j and phi k just don't overlap right, and you get exactly zero. And that's why the symmetry is so incredibly important, because if you don't have any overlap in between those two wave functions, if one has an odd symmetry and one has an even symmetry, you're guaranteed when you integrate them up you're going to get exactly zero, and nothing happens. Only when they don't integrate up to zero does something interesting happen. So we can now take this to the concept of hybridized orbitals. So let's take a p orbital system here where I have sort of a 2s and a 2p, and I'm interacting with a 1s type system over here on the right. So I've got a 2s and a 2p orbital. I've got some z components of angular momentum, -1, 0, +1, and basically I've got the s orbital down there, the p orbital, the pz orbital up there, and then the p plus or minus 1s that are oriented in the other direction. And over here on the right I've got a 1s orbital. Now the first thing is that these tend to line up at roughly the ionization potentials of the frontier orbitals, the highest energy electron in the system. And the idea here is that to first order, every single highest energy electron in a neutral atom or a neutral fragment pretty much thinks it's trying to be a hydrogen, right? It's coming into, if you think of that last electron in, if the system is overall neutral, the last one in encounters something of a +1 charge. It sees a cation with a +1 charge, and to the best of its knowledge, it's looking at a hydrogen. Now obviously as it digs in and generates a wave function, it's going to discover something more interesting than that, but still, to the best of its knowledge, it thinks it's dealing with a hydrogen. And so it's going to have an energy that's something like -1 Rydberg, because that's the energy of a hydrogen. So those ionization potentials typically line up pretty darn well. So if I'm dealing with, say, a hydrogen atom, where I have an electron in a 1s, and anything that has a p shell as the unfilled orbital, but let's think about anything with a 2p that's not complete, then I'm going to pretty much have these things line up at the same energy. And fundamentally, ultimately, the reason why lining up at the same energy is pretty important is it means the spatial extent of those wave functions is going to be about the same. And so as I do these overlap integrals we were just talking about, they're going to be well matched to each other, and I'm going to get lots and lots and lots of overlap, and that overlap is fundamentally what's going to drive this problem. But first we're going to talk about things that don't match up really well. So there's my 1s orbital. Now let's look at a situation where I try to match up this 1s orbital with one of those pi's, with one of those p plus or minus 1 orbitals. Well, those guys have some positive sign on the top, some negative sign on the bottom. My 1s orbital is happily symmetrical, it's only one sign. And those don't have any spatial overlap because they are symmetry orthogonal. They are just plain orthogonal with each other. And nothing I can do with any kind of symmetrical perturbation Hamiltonian is ever going to make those guys have any overlap at all. And so they are strictly zero. They just don't interact with each other in any significant way. That, again, is why we care so very much about this symmetry. Those guys go to zero. So then I have to look at the sigma-type orbitals that I have in the system, because fundamentally what I want to do is stabilize these things. So that first interaction of the 1sa, say with a 2p plus or minus 1 on nucleus B, that was 0. But what I'm trying to find are systems where that overlap is large, where it's large in space and there's not symmetry requirements that make it go to 0. So if we look at these sigma type orbitals, then I've got some interesting overlap potential. But what I can do, and what we do, the reason we hybridize this, is if I want to think about the overall stabilization. Let's say I've got 3 electrons to deal with, and I've drawn them here. I can try to think of the interactions of this 1s orbital. Remember, I'm trying to construct a molecular orbital that's more or less orthogonal. I can think of the interactions of the 1s orbital on the right, and that 2s orbital on the left, and the 2p sigma orbital on the left, and each of those individually, and try to work out all of those interactions that ultimately wind up in figuring out the ultimate energy. And that's a lot of work. Or I can try to localize all of those overlap interactions into one system, one term, and leave everything else as it is. And that's fundamentally why we hybridize this system. So if I take the 2s2 and the 2pz orbital that has sigma symmetry, I can construct these sp hybrid orbitals out of that. And when I construct the sp hybrid orbitals, I've made one orbital that's physically facing the 1s orbital that I'm interested in overlapping with. So those two sp orbitals have basically the same energy. It's basically the average of the 2s and the 2p energies. But now, when those orbitals face that 1s orbital over on the other atom center, the sp positive that's facing the 1s orbital, that has all that spatial overlap. And the spatial overlap is what determines that stabilization term. And of course the destabilization as well. So it splits. And that splitting defines the bonding character of the interaction. So the energy of the sp hybrid itself compared to the s and the p, that didn't change much. So I don't change the overall average energy of my electrons by saying, they're an SPs versus an S and a P. But I do change things a lot by then letting one of those sp, the sp positive, interact with the 1s orbital and do all of that stabilization. And that makes my nice, fatly stabilized sigma bond hybridizing with the sp orbital in the heteronuclear diatomics, where I have interactions between orbitals of different fundamental energies and states. And again, the reason why we line up the energies is because the spatial part of the integral lines up well. Their wavelengths are similar, and so where they're positive, they're going to be positive. Where they're negative, they're going to be negative, and they're going to line up well. And I get a lot of stabilization out of the deal. On the other hand, the sp that's facing in the other direction, there's no overlap at all, and nothing happens. That's a non-bonding interaction, and we draw that molecular orbital at basically the same energy as the sp in the first place. So we generate that stabilization, we figure out what it is, and we get this succession of sigma character bonds with the appropriate amount of splitting and stabilization. That is fundamentally why we generate these hybrid orbitals.